Hello, everybody again. This is going to be a fun one. This is a quick little cursory introduction to a whole field of physics called thermodynamics. Thermodynamics is the study of energy, and that's what we've been studying, right? So really, we have been doing thermodynamics this whole time. We're just going to try now to quantify some of that extra stuff, heat, the thermal energy, that extra loss of energy. Whenever things happen, we have any sort of processes, we lose some heat somewhere. We lose some energy, sorry, and we lose it to the outside system. We have friction. Nothing actually happens at 100% efficiency. We have to take that into account somewhere. So let's talk about some of the laws of thermodynamics. And this is not a straightforward concept, and it's taken a very long time to come up with these, and they're pretty intense things. Like I remember I took a third year thermodynamics class that was one of my most difficult courses. It's a very non-intuitive field of physics, and we're going to try to talk about some of the bigger ideas, and they're incredibly fundamental to pretty much every physical process that happens in the universe. All right, so there are these four laws that we have to talk about that we have to have sort of supersede all of our other laws. They're even more powerful, you could argue, than Newton's law. Newton's laws are possibly just they happen to because of this. Okay, so this has been going on for quite some time. From we have Helmholtz and Boltzmann, Ludwig Boltzmann. Boltzmann, very famous for his Boltzmann distribution of energy that we actually I showed you in the lesson on energy. Right, this guy looks kind of like Bergeron. Scary. And then we're even up to now when we're talking about quantum mechanical energy states and looking at thermodynamics from a statistical point of view. When you talk about a mass of air, you're talking about 10 to the 24 molecules bouncing around. So we have to start applying some statistical analysis and probabilistic analysis to these things. We're not going to get into that. We're just going to do a very quick summary of thermodynamics. Okay? So now I'm going to say there's four laws. This might bother you, but we're going to start with the Zeroth Law. Not the first law, the Zeroth Law. And it's because it is such a fundamental law and it makes so much sense that it's no point of calling it the first law, because it's such a fundamental idea of thermodynamics. Okay, so if we have two systems that are in thermal equilibrium, what the heck does thermal equilibrium mean? For us, that just means same temperature. Okay, that's really all I'm trying to say there. It's more complicated than that, but who cares at the moment? Okay, so basically we have two things that are at the same temperature. So let's say A and B. Whoa, that got really weird. Sorry. A and B. Okay, A and B here are at the same temperature. So these guys are at the same temperature. All right, and that means that if A and C are also in thermal equilibrium at the same temperature, then B and C have to be in thermal equilibrium at the same temperature. Two systems that are in thermal equilibrium with a third are in equilibrium with each other. So all of these things have the same sort of temperature. And it's such a fundamental idea that temperatures equilibrate. Temperatures tend towards equilibrium. If I have a hot cup of coffee, it eventually will approach room temperature, right? It'll approach exponentially, right? There's my 100 degrees. This is my room temperature, and there's a horizontal asymptote, and it approaches that temperature there. Okay, and so it'll equilibrate energy. They want to get into equilibrium. All right. So that's our very, very fundamental law. First law, we have actually already discussed it. It was one of our lessons. Was the conservation law of energy. Right? Energy cannot be created or destroyed. It can only change forms. Right? We already talked about that. We already said that this is this fundamental law that we can't do magic when we do physics. We have to do the accounting. Okay? Now, we're going to change this a little bit because previously we had just said that a change in energy is work. Right? So we had our work energy theorem. We're going to change that slightly. And we're going to say that, in other words, any change in a system's internal energy. Okay, so that's the, now when we talked about work, we talked about doing energy, moving something and putting energy into the system. Okay. Now when we talk about a change in energy, that's the work that was done by the system. Not that we're doing onto the system, that's work done by the systems. That's why that's negative now. Previously it was just delta E equals W, but now it's delta equals negative W because it's work done by the system. And we're going to add now this thing, this idea of Q, that's heat. So the change in its internal energy is how much heat I add to it and how much work I do. Okay? So this is a very powerful equation, and it can answer a bunch of interesting ideas for us. Here's a fun question. It's a hot day outside. Okay, it's the middle of summer. I'm really hot. I'm just going to open up my fridge. That's going to cool down my house, right? My fridge will cool down my house. Will it cool down the house? Any guess? It won't. It'll actually make your house hotter. Okay? And that has to do with how much work you can do and how much heat is added. And it goes to the next law that I think, in my own personal experience, my own personal opinion, is the most fundamental law in physics. It's called the second law of thermodynamics. And it can be stated quite simply as the entropy in a closed system is always increasing. The disorder in any closed system always tends to a higher state of disorder. Now, what the heck does that mean? You can think of it like this. Think about your room. I put a whole bunch of work into cleaning my room. I do a whole bunch of work, and I had to do that work, and my room is now in a state of higher order or lower entropy. Okay, it's in a low entropy state. Now, if I leave it and I just go about my ordinary day doing stuff, my room ends up dirty. Or even my house. I have 4 children. So I spend a lot of time cleaning. And then magically, everything just, gets dirty again and disordered. Because that's the natural way of things. And you can tell your parents, why is your room dirty? Well, the second law of thermodynamics defined that it has to be dirty. But then they're just going to tell you, well, now you have to do work and clean it again. Okay? And another way we can think about it, the second law of thermodynamics is that anytime I perform an energy transformation, anytime I do something, there has to be some inefficiency. There has to be some energy lost to entropy, to disorder. I have to continually, anytime I do something, I'm always losing some of my energy. I cannot have a perfect transformation of energy. There's always going to be some lost somewhere. Okay? This is the second law of thermodynamics. And it's fundamental in almost everything. We can never have a perpetual motion machine. We can never create a machine that runs forever. Because always, at some point, there will be energy lost to the system. The whole system itself has to always have entropy increasing. The universe, if we consider the universe a closed system, all approximately 14 billion light years of the system, it has to be increasing disorder. Okay? This is an incredibly fundamental law. We can never have 100% efficiency. So we can say that no 100% efficient processes. Okay? That's one of these awesome laws of the universe. Now, here's a good quote. Okay, I'm going to read this to you slowly. Okay, so this is from a guy called Sir Arthur Stanley Eddington. Eddington was a very famous physicist from the late 19th century, early 20th century, and he has this quote here: "The law that entropy always increases." So, second law, I think. The law of entropy always increases holds, I think, the supreme position among the laws of nature. If somebody points out to you that their pet theory of the universe is in disagreement with Maxwell's equations, then so much the worse for Maxwell's equations. If it is found to be in contradiction by observation, well, these experimentalists do bungle things sometimes. But if your theory is found to be against the second law of thermodynamics, I can give you no hope. There is nothing for it but to collapse in deepest humiliation. So, the second law of thermodynamics is possibly the most important physical law. Some physicists believe that the second law of thermodynamics is the reason why we have time. Why time is always in one direction. We're always going from the past to the present to the future. We're always going in that direction. Time's arrow. Okay, we call this time's arrow. And it has to do with time's arrow is in that direction of higher entropy. Time's arrow is in the direction of more disorder. Okay, that's the second law of thermodynamics. Last one, third law. This one's a bit sketchy for us. It's a little bit more difficult to understand, but it states that the lowest temperature that you can ever reach is negative 273.15 degrees Celsius, or, in other words, 0 degrees Kelvin. It's called Nernst's theorem. And not only is that the lowest temperature, it's actually impossible to get there. The closer and closer you get there, the more the system wants to fight you and the more energy you have to supply to get it there. It's infinitely, you're going to continually, it's at 0 degrees. This graph helps you understand what this is saying. So if, let's say, we're going to define a lowest state that we can get to. Okay? We're going to define this lowest state that we can get to. That means that let's say that there's more than one state. There's more than one lowest temperature state at t equals 0. Okay? I can get there by a finite number of steps. I can go from x state 1. Whoa, what happened there? I can go down here, and I can get there. However, if I state that there is one lowest energy state possible, there is an absolute 0, I am going to forever bounce between these. I'll get closer and closer and closer and closer and closer and closer, and I will approach it. And we've done this in labs. We have approached this. We've gotten to billionths of a degree away from Kelvin, cooling things down with lasers, stealing kinetic energy with with light, with the wave interference of light, and being able to get single atoms down to billionths of a degree away from absolute 0. But we can never get there, because the closer and closer you get there, the more the system fights you and tries to get you to go away from that. So that's the third law. The lowest temperature is 0, and we can never get there. Now, I did find this interesting thing on the internet, which states that these laws can be put into a very simple form. The Zeroth Law states that there is a game, right? We have this thermal equilibrium problem, so that's our game, that thermodynamics exists, basically. The first law says you can't win. Why does that mean? The first law says that, right, you can't win, which means you can never cheat. You can never get more energy. We're always going to have to balance out what we put in and what we get out. And the second law says you have to lose. We have to lose energy somewhere. You can't win the game, but more importantly, not only can you not tie the game, you have to lose it. And the third law says you can never quit. We can never get down to absolute 0. So there is a game, you can't win it, you have to lose, and you can't quit. That's thermodynamics in a nutshell. Okay? Now, let's go away from this more metaphysical sort of idea and this theoretical view of what is thermodynamics, and let's go to a little bit more a simple idea. Okay, so heat. We've talked about heat. You can increase and lower the heat of something. Let's try to quantify. Let's try to get a mathematical expression that can help us understand heat. And how are we going to determine the amount of heat that is added to a system? Okay, so we know the heat is measured by the amount of motion of the atoms involved in the system. The more heat I add to something, the more the atoms are going to move around. I start boiling water, start warming up water, the atoms in the water start moving around until to the point where they get to the point that they break free of the surface of the water and they become a gas. And then they have lots of energy and they whiz around all over the place. So motion, or average temperature, what we call that, this idea of temperature and average kinetic energy, tells us that heat has to be proportional to the temperature. As I increase my heat, my temperature also increases. As I increase my temperature, my heat increases. Also, the more atoms that are there, the more difficult it is to increase that kinetic energy. So the more mass that I have, the more energy that I have in the whole system, or thermal energy. If we have a small cup of water, right, or a cup of coffee, it will cool down, at a reasonable rate. But if I have a whole big kettle full of hot boiling water, that will slow down slower. That'll cool down slower because there's more mass. All right, so I can put these two together into this equation here, that the heat can be calculated to be the mass times the temperature times this constant, which we call the specific heat of the material. It's defined to be the amount of energy in, let's say in this case, kilojoules, that can increase 1 kilogram by 1 degree Kelvin or 1 degree Celsius. Okay, 1 Celsius or Kelvin, they're the same thing. Okay, now water here, for example, has the specific heat of about 4 kilojoules per Kelvin per degree Celsius. So for me to, that just tells me if I have a kilogram of water, so a liter of water, and I want to increase it by 1 degree Celsius, I have to give it 4,000 joules. Okay, water has quite a high specific heat. Right, it stores energy quite well. We know that when we go to in the summertime, you go to the lake, you go to the ocean, right? Because that's storing that heat, and it keeps things cooler, right? Most solids actually have a much lower specific heat. Here, if we go here, look at this table. This shows us things like metals here have specific heats in the region of 0.4 or something like that. Whereas when we get to water, it has quite a high specific heat. And that has some very important implications in biology and ecology, and the role that water has in moderating temperatures, moderating weather, and basically defining our life. Okay, so the fact that water has such a high specific heat is actually really important, but beyond the scope of this course. Okay, so here, for example, here's a couple: iron, 0.444, about a tenth of water. Gold has a very, very low specific heat. Another way you can think about this is also conductivity. We know that metals conduct heat a lot better than things like plastic. Okay, and that has to do with the specific heat. So this leads us to a fun little question here. I'd like you right now to put your hand on something metal. Right, touch something metal here. I'll grab the leg of my desk here. Okay, and then with your other hand, touch something plastic. Which one feels cooler? Which one is colder? Which one do you think? The answer is they're actually the exact same temperature. Yeah. And you can take a little device and measure the temperatures, and they're the exact same. And this has to do with the fact that the metal has a lower specific heat. It takes less energy to warm it up from room temperature to the temperature of my hand. Both of those plastic and metal objects are about 21 degrees. Your hand is about 28 degrees or something like that, or much higher. So when you put your hand on it, by the Zeroth Law, it's going to take heat away from your hand. It's going to want to equilibrate. It's going to want to bring your hand and the object to the same temperature. However, the specific heat of the metal is much lower, so it's much easier to change its temperature, so it takes the heat out of your hand at a higher rate. So it's not actually feeling colder, it's just that it's taking the heat away from your hand faster than the plastic's able to. Okay? So it's taking the heat away from your hand, and it tells our nervous receptors that feels cold. It's a really interesting idea that even though metals, they feel cold, right? It's winter time and you're in grade 1 or something like that, and the teacher goes and tells you, don't lick the metal pole. Why wouldn't you lick the metal pole? What's going to happen? It's going to take the heat away from your tongue very rapidly and freeze the water on your tongue very rapidly, and your tongue will stick to the metal pole. And then your teacher's going to have to go and get a hot water to get it off your tongue, off the pole, or bad things happen. Okay? So, interesting idea here, the specific heat and how it affects things. Let's do a quick little math problem here. What is the amount of energy required to increase the following by 10 degrees? Water. So, Q, right? Oopsies. Which way are we going here? So, Q is to A here. Is equal to MC delta T. Right? The amount of heat. So let's assume 1 kilogram to make our lives easier. Okay. So we know, if I use my table, that the mass is 1. C is 4.18. What's that? It's going to be kilojoules per kilogram degree Celsius multiplied by 10. So that's going to work out to 41.8 kilojoules. That's how much heat I'm going to have to require to heat up a kilogram of water. What about a kilogram of glass now? Same idea. Q equals MC delta T. It's a fun equation to memorize. Let's go back here. Glass. 0.84. So again, 1 kilogram, 0.84 kilojoules per kilogram degrees Celsius times 10 degrees Celsius. Oh, I forgot that over here. Terrible, Mr. Stone. All right, so that's going to be 8.4 kilojoules of energy. Okay, that gives you an idea of how much more energy is required to heat up water than glass. Okay, so Q equals MC delta T. All of these are scalars. Don't worry about that. Oh my goodness, Mr. Stone, you are terrible. What have you done? Temperature is a capital T, not time. Okay, capital T for temperature. All right. You may have noticed, though, if I go back here, this gives us a slightly different unit, joules per gram Celsius, whereas I'm using kilojoules per kilogram, and it doesn't matter, right? Because 1 kilojoule per kilogram, a kilojoule is 1,000 joules, and a kilogram is 1,000 grams. So the thousands cancel, and we get joules and grams. So you can either use whatever they give you. If they give you kilograms, use kilojoules per kilogram. If they give you grams, use joules per gram. Okay, either one will work. Okay, so last example before we go on some homework problems. Let's say I take a 50-gram block of nickel. Okay, 50-gram block of nickel. I heat it up to 2,000 degrees Celsius. That's a really hot ball of nickel. And I drop it into 1.4 kilograms of water, so about 1.5 liters of water. What's the new temperature of the water? How much does the temperature increase? Anyone want to guess? Quickly, just guess quickly. Okay, let's calculate this. Now, we know from the second law, the first law. The first law of thermodynamics states that the energy that I gain in the water and the energy that I lose in the nickel have to be equal to 0. This is my first law. I can't gain or lose any energy. There is no, this is telling us that energy is not created or destroyed. The balance has to equal 0 in the end. So another way you can say this is that the energy gained by the water is equal to the negative energy or heat lost in the nickel. Okay? So let's use our new formula that the mass of the water multiplied by the specific heat of the water times the change in temperature of the water, it's going to be equal to negative mass of the nickel, the specific heat of the nickel, and the change in the temperature of the nickel. Okay? So this is saying that the energy that I lose in the water is going to be the same as the energy gained by the nickel. Sorry, the energy lost by the nickel is the energy gained by the water, right? Because of the Zeroth Law. It has to equilibrate. They have to end up at the same temperature. So using that same idea, I can rewrite delta T as the mass of the water, specific heat of the water, and this is going to be the final temperature take away the initial temperature of the water. Okay, let's call TF the final temperature of the water, also the final temperature of the nickel. Very important point there. And TW being the initial temperature of the water, which is, we're going to assume that the initial temperature of the water, let's say room temperature, 21. And this here is going to be the temperature of the nickel to begin with. Oh, lowercase n I'm using. Okay, so that's going to be equal to negative mass of the nickel, specific heat of the nickel, again, the final temperature minus temperature of the nickel. And notice here, I have a final temperature and a final temperature on both sides. They're going to be equal. Okay, by the Zeroth Law, the fact that the temperatures are going to equilibrate at the end, those two temperatures have to be the same. The temperature of the water after everything's equilibrated is going to be the same as the temperature of the nickel. All right? So now I have to do a little bit of algebra and rearrange these equations to get this to work out. So how's that going to work? I'm going to have to multiply this into both. I'm going to expand both these brackets. I'm going to do my rainbows. Okay, so what am I going to end up with there? This is going to get a little bit messy, let's say. Okay, so that's going to be the mass of the water, especially writing it on a laptop screen. Temperature final, take away mass of the water, specific heat of the water, temperature of the water is equal to negative mass of the nickel, specific heat of the nickel, temperature final, plus mass of the nickel, specific heat of the nickel, temperature of the nickel. Right, notice negative times a negative gave us a positive. Okay, so we're still looking, the idea was to get TF, isolate TF. We're doing a little solving here. I got a TF there and a TF there. Why don't we bring all the TFs together and all the other things on the other side? So I have this guy here still, mass of the water, specific heat of the water. Can you guys see that? Yeah. Temperature final. I'm going to bring this one over, so that's going to become positive. Mass of nickel, specific heat of nickel, temperature of everything at the end. And I'm going to bring this, the water term, the TW term, over to this side. So I'm going to get mass of the water, specific heat of the water, temperature of the water. Notice it was negative. I brought it to the other side. It became positive. And then I have this last term, mass of the nickel, specific heat of the nickel, temperature of the nickel. Okay? So I'm getting there. I got the TF at least on one side of the equation. So why don't I factor out my TF? I'm going to switch over to here. I'm going to have TF outside. I'm going to be left with the mass of the water, specific heat of the water, plus the mass of the nickel, specific heat of the nickel. I've factored it out of both. This is going to be equal to the mass of the water, specific heat of the water, initial temperature of the water, plus the mass of the nickel, specific heat of the nickel, initial temperature of the nickel. And then I can divide both sides of the equation by that bracket. Whoopsies. Mass of the water, specific heat of water, mass nickel, specific heat of the nickel, mass water, specific heat of water, mass the nickel, specific heat of the nickel. Now, you would think it'd be nice if things would cancel here. These two brackets are exactly the same, but they cancel. There's no canceling available here because of these temperature terms in there. They're not the same, so we can't factor anything out. We can't cancel. Sorry, it's messy. So our final expression is temperature final. The final temperature of both the nickel and the water is going to be, what is that? Mass of the water, specific heat of the water, temperature initial of the water, mass of the nickel, specific heat of the nickel, temperature nickel, all over. Mass of the water, specific heat of the water, mass of the nickel, specific heat of the nickel. Okay? And once you plug all these guys in here, work it all out, we get a new temperature of 28 degrees Celsius. I'll let you guys figure that out. Plug into that formula. But my 21 degree water, when I dropped 50 grams of 2000 degree nickel into it, only increased by 7 degrees. Change in temperature of the water was only 7 degrees. That shows you how much, what the high specific heat of water can do. Okay, there's a lot more of it, but that high specific heat of the water meant that it only changed a little bit. You can cool down metals quite quickly with a bucket of water. Okay, and that has to do with the fact that the specific heat of the water, whoa, that's hideous. Speed of the water is much less than the specific heat of nickel by a factor of about 10. Okay? So I'll let you guys can plug that in to check my work. Please check my work. It's Mr. Stone. You never know. Okay? So now what I'd like, practice questions 10 through 16. I will post those on the Weebly. Okay? And I'll post the solutions as well. And good luck. And I hope you guys are all well. Hope you're all healthy. Don't stress too much. Stay safe. Stay home. Do physics. All right. And before we go, here's a quick little quote from Sommerfeld. Now, thermodynamics is a funny subject. The first time you go through it, you don't understand it at all. The second time you go through it, you think you understand it, except for a few minor details. The third time you go through it, you know you don't understand it, but at that point, you're so used to it, you don't bother. It doesn't bother you anymore. Okay, thermodynamics is incredibly non-intuitive. It's very difficult to wrap your head around. So don't worry too much. This is a quick little overview of it, of some of the ideas of our 4 laws, 0, 1, 2, and 3. Sorry about the 0. It's a bit weird, I know. And just keep in mind that second law of thermodynamics is, in my opinion, the most fundamental law in the universe. Okay, well, I'll be signing off for now, and see you later.